The knowledge transfer algorithms in federated learning are, I think, the source of many of its privacy and security vulnerabilities. And if you want to design collaborative learning systems which are robust to all different attacks, we need to find a different knowledge transfer algorithm, and this is what I'm going to present, one attempt towards replacing the existing techniques with something which is very simple to implement but is more resilient to attacks. The primary principle of collaborative learning is sharing without sharing. We have participants with sensitive data. They do not want to share their data with each other, but they want to share the knowledge that they have towards training a global model. So we can design a decentralized training algorithm to gradually lead them towards that global model. And the way that is done, the widely used technique, is to share the parameters of a local model which is trained on the local data with the server. The server does the element-wise averaging of the parameters and send it back to the participants. They override the local models with that, and then they go over the next round of training. The question is, why do we share the parameters? Why do we do the knowledge transfer through exchanging model parameters? Is this the only way to do knowledge transfer? Is this the desirable way of doing knowledge transfer? Definitely it is not desirable, because it's a source of so many issues. There are communication overheads of sharing large model parameters, and there's a large body of work on how to compress model parameters, how to encode them in a way that you don't lose the model accuracy, but at the same time they would be able to converge on a global model with minimum communication overhead. As the models completely expose as the participants completely expose their local models to the parameter server and also to the other participants in a more indirect way, the attacker can run so many inference attacks to learn the latent features of the model's training data, to learn what data is in the training set of participants, what are the attributes of that data, what are the properties that apply to the population of the data and different participants' training sets. And protecting the privacy in this setting where you want to share the whole parameter vector is also very difficult. If the attackers are not only curious, but they want to also damage the global model, they can do it very easily, because they can influence the aggregated parameters, and this would be used to override the local models of all participants. So effectively the attacker only needs to defeat the aggregation algorithm, and using different types of data poisoning and model poisoning attacks. Many papers have shown that these attacks are possible even in presence of some robust aggregation algorithms. And also limiting the knowledge transfer to element-wise aggregation of the model parameters would restrict these networks to homogeneous models. So different participants cannot have different model architectures because it's impossible to aggregate them in an element-wise mean computation of their model parameters. So let's go through some of these issues, in particular the privacy and robustness issues, and then we come back and see how we can redesign the knowledge transfer algorithm. If an attacker has access to the model parameters, which is trained on a particular training set, he can ask many different questions. He can ask whether the particular attributes of the training data, he can ask what data point is part of the training set, and so on and so forth. In the membership inference attack, the attacker wants to know whether a particular record is part of the training set. And this is shown time and time again that is possible because the trajectory of the model parameters during the training is completely decided by the training data. So if one data point is part of the training set, it's going to have an influence on the model parameters, which will be recognizable by the attack. So if you look at the model parameters, then compute the gradients of the model on different data points, then just even the norm of the gradients on the training data is much smaller than the norm of the gradient on the data outside the training set from the same population, because the model is reducing the loss on that data, but not necessarily on the whole population. So these signals could be used to run membership inference attack on the trained models. And here is the result of the attacks that we had on pre-trained models, the best models which are trained for different architectures out there. For example, for DenseNet, which gives a very good accuracy, we see that the privacy is pretty low in the white box setting, and this is more or less because of the large capacity of these models. So the larger the capacity is to enable searching for optimal model, the higher is the risk of sharing that model parameters with others. In the case of federated learning, the adversary, whether it being the parameter server or the other participants, would not observe only one snapshot of the target's model, but multiple updates. Because at every iteration, you update the model with the same training data and send it to the adversary. The adversary can look at the trajectories of the change and infer information about which data is part of the training set. And one observation that we have, which is aligned with many findings in the machine learning community, is that in the early epochs, the models learned the general patterns, but later on, they try to fit all the atypical data, and therefore the leakage in the later stages of the training is more. One other property of federated learning based on sharing model parameters is that the attacker can also influence the target's training, because the attacker could be a participant in the network or the parameter server, so can change the parameters that one particular party is going to use to initiate the next round of local training. And the question is whether those kind of active attacks using model poisoning would enable the attacker to infer even more information about the training set of some target models. Again, we go back to the training algorithms that the local participants are using. And in this very high dimensional space of parameters, if the attacker increases the loss on a target data point using gradient ascent, this change would remain undetected by any party, and during their local training they're not going to fix this unless they have that data point, that target data point in their training set. If they have that target data point in the training set, they're going to reduce the loss on that and basically will correct this change which was imposed by the attacker. Therefore, the attacker can look at the change and compare this change with the change on the model parameters with respect to other data in the population, and can infer if this data point has been part of the training set. And yes, this can help a lot in increasing the accuracy of the inference attack. For example, in the case where the parameter server is the attacker, it can even isolate a target model, run this gradient ascent attack, and get an accuracy above 90%, which is a very large accuracy for membership inference attack. Continuing on the line of active attacks, if the attacker's objective is to impair the global model and later all the models which are going to be used by the local participants, he can do so by basically trying to attack the aggregation algorithm which is used. We know that element-wise mean is very vulnerable. One single participant completely changed the result. So there has been many suggestions on replacing this aggregation with more robust aggregation algorithms using element-wise median or computing geometric mean, filtering out data which is away from the median vector, and so on and so forth. And some of them are coming with robustness guarantees, but unfortunately in this very high dimensional space of model parameters, million dimension, the error guarantee is not very tight, as it is proportional to the square root of d being the number of dimensions. So this would leave a lot of space still for the attacker to manipulate all the models by changing the model parameters gradually. The attacker can prevent the convergence of robust aggregation algorithms or just completely divert the parameters away from the optimal values, or embed some adversarial backdoors into the models. Given this set of vulnerabilities, we want to rethink the knowledge transfer algorithm, which is based on the most basic way of doing it. So we are just sharing the models and overwriting the local models with the aggregated models. I'm going to talk about another simple knowledge transfer algorithm, which is more robust against the attacks. So the idea is that instead of sharing the model parameters, the participants share their predictions on an unlabeled public data. And so the predictions, they can just share the prediction vector, and then the aggregator will just compute the robust mean of these predictions and send the soft labels for the public data to the participants. And what they do is that in each round of training, they train on the union of the local data and the labeled public data. So here what is very interesting is that in the case of using this black box knowledge transfer distillation algorithm, the model structures of course could be heterogeneous because we are aggregating the model predictions. So the parameters and the model structures and the type of the models could be different. Different participants could be running different models. And also the information leakage is limited because we only leak as much as the black box access to models leak. Definitely the attacker is not going to get information about the latent features of the data and so on. And basically the robust aggregation of these prediction vectors is much more resilient to attacks because of the low dimensionality of the prediction vectors. So we can actually come up with very tight error bounds with low sample complexity. So smaller networks could be resilient to attacks. And this robust aggregation would prevent many data and model poisoning attacks. The other property is that because the models are not going to be overwritten directly by the global model, and there is this training and fine-tuning that happens based on the labeled data, then the influence of the attackers is also much less. Designing the attacks are also more difficult. So we tested many existing poisoning attacks, all the strong poisoning attacks that are designed in the literature, against different federated learning algorithms and also Cronus. And here I show you the result of the strongest attack against each federated learning algorithm. And obviously in the adversarial setting, Cronus is the strongest algorithm. The others would have a much less accuracy, many of them random guess accuracy in presence of the attack. Here, one detail that I want to mention is that the number of adversarial parties are not the same for all these different algorithms because they have different breaking points. So some of them, if you have more than half of the participants being adversarial, then they break. So we cannot have any robustness guarantee. But for some of them, for example, Boolean has much smaller breaking point. So if you use the same breaking point, if you use the same number of adversaries that we use against Chrome and Cronus, then Boolean will just give you no accuracy. So obviously Cronus is more strong than others and more robust, and the other experiments on other datasets also show the same result. Against membership inference attacks, again we'll see that Cronus has a much less information leakage about the training data compared to federated averaging. So federated averaging for these two datasets that we tested is resulted in about 80% accuracy of the inferring members of the training data, which is a huge number. And the membership inference accuracy for Cronus is around 55%. Note that 50% is the random guess, which is the best privacy case. So to conclude this, I want to go back to the first point that I mentioned, that sharing the knowledge using the parameter exchange for federated learning is not necessary. So there are other ways that you can do knowledge transfer. It is definitely not efficient because for large models we have to deal with all the communication overhead. It is not robust because the attacker has a lot of influence on the other models, and also in that high dimensional space, coming up with tight error guarantees is very difficult. It's not privacy preserving because the models leak a lot of information through their parameters. And also protecting them using differential privacy and other techniques is also very difficult. But protecting the model predictions is easier. Also, the model parameters used as a knowledge transfer is not a flexible technique because it doesn't allow heterogeneous models to be used. So I think Cronus, using the known knowledge transfer of black box models, and distillation techniques is a very promising direction towards solving many of these issues. There has been a lot of progress in improving these knowledge transfer algorithms in the ML community, and there has been a lot of work also improving the robustness and the privacy of models in the black box setting. And I think if all these combine would allow us to train more robust, privacy preserving, and flexible and scalable federated learning networks.